The first section that we're going to look at is the mean and the variance of random variables. So the mean of any random variable, also known as its first moment, is basically denoted as the Greek letter mu. And specifically, we're going to say that mu is equal to the expected value of x. It literally is just the expected value. It is the average possible outcome of a given random variable. So in this case, the mean is the expected value. Pretty straightforward. The variance of a random variable gets a little bit more complicated, and it's ultimately a measure of how spread out a random variable is from its mean. So if we look at some quick examples here, let's say that we have a general PMF, and that PMF has a graph that looks something like this. In that case, we can say that that has a mean that sits right around here, and that's great. But what about a PMF that looks something like this? Well, that also has a mean that sits right around the same point for all intents and purposes. Let's say they are the same point, but those are different PMFs. They have different values. And so we need a way to measure how far it is from the mean to each of those extremes. And variance gives us a way to do that. It's a measure of the spread of a random variable about its mean. So the absolute average value of the distance from the mean is more important, because if you were to look at this and just say, hey, what's the average value of the distance from the mean? Well, that would average out to the mean, because at the end of the day, it's the mean. Now, what we care about is the absolute value of that average, and specifically the distance from the mean there. So when we talk about the absolute value, we're looking at how far is it, whether it's positive or negative, how far is it each direction from the mean. Now, to do this, we need a couple of equations, and the first one is going to be just the expected value of x, and we've seen this before. It's the sum over all possible x of the actual value of x times the probability mass of that variable x at each possible value or each possible outcome of that random variable x. Now, the second equation that we'll use is the expected value of x squared. Now, this is specifically of the square of the random variable. We'll see later that we're going to need the square of the expected value, and that one's relatively easy to compute. But for now, what we'll look at is just the expected value of x squared. And this is the sum over all possible values of the random variable x of the square of the value of x at this instant multiplied by the probability mass of that specific value. So pretty straightforward. This should make sense based on the first lecture of this week, where we talked about how to perform how to perform a function of x. This is really just g of x is equal to x squared. Nothing super crazy, just applying that to the expected value now of x squared. Now, based off of this, we can utilize these two values to calculate the variance. And the variance in this case, we're going to give two different ways that you can calculate the variance. And the variance is written just as the variance of x, or the VAR of x. And that can be utilized in two different ways. We can calculate it two different ways. And the first is this formula right here. It's the expected value of x squared minus the expected value of x, then squared. The other way to look at this is just the expected value of the distance of x from the mean squared. Now, this equation here on the right probably makes a little bit more sense. It's a little bit more like what we were talking about up here when we said that we're looking for the average absolute value of the distance from the mean. And so we can go through and very quickly see that this equation here on the right works. But what's more important is that we look at this as a sum of moments, or more accurately, a difference of moments. When we look here, and these two terms work together to give us the exact same value. Now, we're not going to go through a proof of how that works, but feel free to work through that on your own if you would like to. The last thing that we'll look at is how we can scale a variance. And so to do this, again, we're not going to go through a proof here, but we can say that the variance of a linear function of x. So we'll say that it's a multiply of a, and then we're going to add an offset of b. So if we take the variance of some random variable, some linear equation applied to a random variable, we can say that the variance of a given ax plus b is equal to a squared times the variance of x. And this makes sense because if all values of x have a common offset, well, then the mean, our mu, is just going to shift and get pulled out of every single one of those. So it doesn't really have an impact on the variance when you add an offset to your random variable. Now, because the variance is a square of x, every multiplier, every scale factor against x, this a and the ax plus b, will be squared when you pull it out of the variance. So again, we can say that the variance of ax plus b is equal to a squared times the variance of x. Now, something to keep in mind is this next thing, standard deviation. But to get there, first we want to look at why we need it. And ultimately, the reason behind it is that the variance squares the random variable, right? We're taking the square of it. And so therefore, the units of that variance are also squared. So if we were to look at this in terms of a basic physics problem, for instance, and say that we were measuring meters, well, as soon as we take the variance of that, we're now at meters squared. And sometimes it's super beneficial to have just a measure that is in the same units so that we can use it as an offset or a scale factor, but not have to worry about the units being different. And so the standard deviation is the way to fix that. And so in this case, we can say that the standard deviation of a given random variable, that is sigma of a given random variable x, is just equal to the square root of the variance of x. Now, it's important that you have the square root of the square because that's how you get your absolute value. If you were just to eliminate from the original variance and say, oh, well, I just don't need to square it anymore, well, now you're no longer getting that benefit of squaring, which is that it gives you an absolute value, an always positive value of each delta from the mean. So again, kind of important to make sure that you calculate the variance first and then take the square root of that to get the standard deviation.